The universe is vast, mysterious, and filled with secrets that defy explanation. What if I told you that out there, in the endless expanse of space, there are phenomena so strange, so baffling, that even the brightest minds on Earth can't unravel them? From invisible forces shaping galaxies to signals from the depths of space that vanish without a trace, the cosmos holds mysteries that challenge everything we think we know. Today, we're diving into 50 of the most perplexing space mysteries that science still can't explain. These aren't just questions about distant stars or alien life. They're puzzles that could rewrite the very laws of physics as we know them. So, are you ready to explore the unknown, to question what lies beyond the edges of our understanding? Stick around, because by the end of this journey, you'll see the universe in a whole new light, and maybe, just maybe, you'll start to wonder if we're truly alone out there. Let's begin. Now turning to the first of our 50 space mysteries, we encounter the Fermi Paradox. Named after physicist Enrico Fermi, this paradox asks a simple yet profound question. If the universe is so vast and filled with countless stars and planets, why haven't we found any evidence of extraterrestrial life? With billions of galaxies, each containing billions of stars, the odds seem overwhelmingly in favor of life existing elsewhere. Yet, despite decades of searching, we've found nothing. No signals, no artifacts, no signs of intelligent civilizations. This silence has led scientists to propose several intriguing theories. One of the most discussed is the Great Filter, the idea that there's some kind of barrier, whether biological, technological, or cosmic, that prevents life from advancing to the point of interstellar communication. It could be that life is incredibly rare, or that civilizations tend to self-destruct before they can reach out to the stars. Another possibility is that advanced civilizations are deliberately avoiding contact with us, perhaps observing us from afar or hiding their presence for reasons we can't yet understand. Whatever the explanation, the Fermi Paradox remains one of the most compelling mysteries in science, forcing us to confront the possibility that we might be alone, or that the universe is far stranger than we ever imagined. Now turning to the second of our 50 space mysteries, we delve into the enigmatic world of dark matter. This invisible substance makes up roughly 27% of the universe, yet it remains completely undetectable by conventional means. We know it exists because of its gravitational effects on the cosmos. For instance, galaxies rotate at speeds that defy the laws of physics as we understand them, unless there's some unseen mass holding them together. That's where dark matter comes in. It acts as a cosmic glue, providing the extra gravitational pull needed to keep galaxies from flying apart. But what exactly is it? Scientists have been searching for answers for decades, yet dark matter continues to elude detection. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. Some theories suggest it could be made up of exotic particles that interact only weakly with ordinary matter, while others propose it might be connected to undiscovered dimensions or even modifications to the laws of gravity. Despite the challenges, researchers are using cutting-edge experiments, from deep underground detectors to space-based observatories, to uncover its true nature. The mystery of dark matter not only challenges our understanding of the universe, but also reminds us how much we have yet to discover. As we continue our journey through these cosmic enigmas, the search for dark matter stands as a testament to humanity's relentless curiosity and determination to unravel the secrets of the cosmos. Now turning to the third of our 50 space mysteries, we explore the perplexing force known as dark energy. While dark matter holds galaxies together, dark energy is responsible for something even more profound: the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant supernova, dark energy makes up about 68% of the universe, yet its true nature remains one of the greatest mysteries in modern physics. Unlike gravity, which pulls objects together, dark energy seems to push space itself apart, acting as a kind of anti-gravity. This mysterious force is causing the universe to expand faster and faster over time, a phenomenon that defies our expectations based on the known laws of physics. Scientists have proposed various theories to explain dark energy, from the cosmological constant, a concept introduced by Albert Einstein, to the idea of a dynamic field called quintessence. However, none of these explanations fully account for its behavior. The implications of dark energy are staggering. If it continues to dominate the universe, it could lead to a future where galaxies drift so far apart that the night sky becomes empty, a scenario known as the Big Freeze. Alternatively, some theories suggest dark energy could evolve in unexpected ways, potentially leading to a big rip where even atoms are torn apart. Despite decades of research, dark energy remains elusive, challenging our understanding of the cosmos and pushing the boundaries of science. As we continue to probe this enigma, dark energy stands as a reminder of how much we still have to learn about the universe and its ultimate fate. Now turning to the fourth of our 50 space mysteries, we delve into the enigmatic force known as the Great Attractor. This mysterious gravitational anomaly exerts an immense pull on galaxies, including our own Milky Way, drawing them toward an unseen point in the cosmos. Located in the direction of the constellations Centaurus and Hydra, the Great Attractor lies approximately 250 million light-years away. What makes this phenomenon even more intriguing is its position within the zone of avoidance, a region of the sky obscured by the dense dust and stars of the Milky Way's galactic plane. This makes direct observation incredibly challenging, as the light from objects in this region is heavily absorbed and scattered by interstellar material. Scientists have had to rely on indirect methods, such as studying the motion of galaxies and mapping the cosmic microwave background, to infer the presence and influence of the Great Attractor. Despite these efforts, its true nature remains shrouded in mystery. Some theories suggest it could be a massive concentration of dark matter, while others propose it might be a supercluster of galaxies with an unusually high density. The Great Attractor not only challenges our understanding of cosmic structures, but also raises questions about the large-scale distribution of matter in the universe. As we continue to explore this gravitational enigma, it serves as a reminder of how much of the cosmos remains hidden from our view, waiting to be uncovered. Now turning to the fifth of our 50 space mysteries, we explore the baffling phenomenon of fast radio bursts, or FRB. These are incredibly intense bursts of radio waves that last just a few milliseconds, yet they release as much energy as the sun does in an entire day. First discovered in 2007, FRBs originate from deep space, often billions of light-years away, making them one of the most enigmatic signals in the universe. What makes FRBs so puzzling is their unpredictability. Some burst once and are never detected again, while others repeat at irregular intervals, defying easy explanation. Scientists have proposed several theories to account for these mysterious signals. One leading idea involves neutron stars, particularly highly magnetized ones known as magnetars. These dense stellar remnants could produce powerful bursts of energy through starquakes or magnetic field interactions. Another possibility points to black holes, either through the collision of two black holes or the destruction of a star by a supermassive black hole, releasing a torrent of energy. And then there's the more speculative theory: could FRBs be evidence of extraterrestrial intelligence? Some have suggested that these bursts might be signals from advanced civilizations, perhaps used for communication or even propulsion. While this idea remains highly controversial, it adds an intriguing layer to the mystery. Despite decades of research, the true origins of FRBs remain elusive. Each new detection brings us closer to understanding these cosmic flashes, but for now, they remain one of the most tantalizing puzzles in modern astronomy. As we continue to unravel the secrets of FRBs, they remind us of the vast, uncharted frontiers of the universe that still await our discovery. Now turning to the sixth of our 50 space mysteries, we delve into the legendary WOW signal, a radio signal that has captivated scientists and enthusiasts alike since its discovery in 1977. Detected by the Big Ear radio telescope at Ohio State University, the signal lasted for 72 seconds and appeared to originate from the direction of the Sagittarius constellation. What made the WOW signal so extraordinary was its intensity and frequency, which matched the expected characteristics of a signal from an extraterrestrial civilization. The astronomer who discovered it, Jerry Amon, famously circled the signal's date a printout and wrote "WOW" next to it, giving the phenomenon its iconic name. Despite its tantalizing nature, the WOW signal has never been detected again, leaving scientists puzzled. Over the years, numerous theories have emerged to explain its origin. Some suggest it could have been a natural astrophysical event, such as a comet or a passing asteroid reflecting radio waves. Others argue that it might have been a one-time burst from a distant star or even a glitch in the telescope's equipment. However, the most intriguing possibility remains that it was a deliberate signal from an intelligent extraterrestrial source. The lack of a repeat detection has only deepened the mystery, as it challenges our understanding of how such signals might be produced and transmitted. Could the WOW signal have been a fleeting attempt at communication from a distant civilization, or was it simply a cosmic coincidence? The debate continues, and the WOW signal remains one of the most compelling pieces of evidence in the search for extraterrestrial intelligence. As we ponder its origins, it serves as a reminder of the vast unknowns that still lie beyond our reach in the cosmos. Now turning to the seventh of our 50 space mysteries, we explore the enigmatic Tabby star, also known as KIC 8462852. This star, located approximately 1,400 light-years away in the constellation Cygnus, has baffled astronomers with its irregular and dramatic dimming patterns. Unlike most stars, which dim in predictable ways due to orbiting planets or natural stellar activity, Tabby's star exhibits sudden and significant drops in brightness, sometimes by as much as 22%. These unusual fluctuations were first observed by NASA Kepler Space Telescope, sparking a wave of scientific curiosity and speculation. One of the most intriguing theories suggests that the dimming could be caused by alien megastructures, such as a Dyson sphere, designed to harness energy from the star. While this idea captures the imagination, other explanations point to more natural causes, such as massive clouds of dust or debris from comets or asteroids. Some scientists propose that the star itself might be undergoing internal changes, releasing bursts of material that temporarily obscure its light. Despite extensive observations and studies, the true cause of Tabby's star's dimming remains elusive. Each new piece of data seems to deepen the mystery rather than resolve it. Could this be evidence of advanced extraterrestrial engineering, or is it simply a rare and poorly understood natural phenomenon? As we continue to study Tabby's star, it reminds us of the countless wonders and puzzles that the universe holds, waiting to be unraveled. Now turning to the eighth of our 50 space mysteries, we delve into the perplexing case of Oumuamua, the first known interstellar object to pass through our solar system. Discovered in October 2017, Oumuamua immediately stood out due to its unusual characteristics. Unlike typical asteroids or comets, this object had an elongated, cigar-like shape, estimated to be about 10 times longer than it was wide. Its surface appeared reddish, suggesting it had been exposed to cosmic radiation for millions, if not billions, of years. But what truly baffled scientists was its unexpected acceleration as it moved away from the Sun. Instead of slowing down as expected, Oumuamua sped up, defying the laws of gravity as we understand them. This peculiar behavior led to a flurry of theories about its origin and nature. Some researchers proposed that Oumuamua could be a fragment of a larger object, perhaps shattered by a collision in its home star system. Others suggested it might be a comet, releasing gases that acted like a natural thruster, though no visible tail or coma was ever detected. The most tantalizing hypothesis, however, is that Oumuamua could be an artificial object, possibly an alien probe or spacecraft. This idea gained traction due to its unusual shape and acceleration, which some argue resemble the design of a light sail, a theoretical propulsion system that uses sunlight to travel through space. While this theory remains speculative, it underscores the profound mystery surrounding Oumuamua. Was it a natural visitor from another star system, or could it be evidence of extraterrestrial technology? Despite extensive observations, Oumuamua has since left our solar system, leaving behind more questions than answers. Its brief visit reminds us that the cosmos is full of surprises, and some mysteries may remain unsolved for generations to come. Now turning to the 9th of our 50 space mysteries, we explore the enigmatic black hole information paradox, a puzzle that pits two of the most fundamental theories in physics against each other. At its core, this paradox revolves around a simple yet profound question. What happens to information when it falls into a black hole? According to Einstein's theory of general relativity, once something crosses a black hole's event horizon, it is lost forever, crushed into the singularity at the center. However, quantum mechanics, the framework governing the behavior of particles at the smallest scales, insists that information cannot be destroyed. This contradiction has left scientists scratching their heads for decades. The paradox gained prominence thanks to the work of the legendary physicist Stephen Hawking. In the 1970s, Hawking proposed that black holes are not entirely black. Instead, they emit a faint radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. But here's the catch. Hawking radiation appears to be random, carrying no information about the matter that fell into the black hole. This implies that when a black hole evaporates completely, all the information about the objects it consumed is lost forever, violating the principles of quantum mechanics. This dilemma has sparked a flurry of theories and potential solutions. One of the most promising ideas is the holographic principle, which suggests that all the information about objects falling into a black hole is encoded on its event horizon, much like a hologram. In this view, the event horizon acts as a two-dimensional surface that stores a complete description of the three-dimensional objects inside. When the black hole evaporates, this information is somehow preserved and released back into the universe, resolving the paradox. Another intriguing proposal is the idea of black hole firewalls, hypothetical boundaries of intense energy at the event horizon that could destroy anything falling in, effectively preserving information by preventing it from entering the black hole in the first place. However, this theory remains controversial as it challenges our understanding of space-time and the nature of black holes. Despite decades of research, the black hole information paradox remains unsolved, standing as one of the greatest challenges in modern physics. It forces us to confront the limits of our knowledge and the possibility that our current theories are incomplete. As we continue to probe the mysteries of black holes, we may uncover new insights that bridge the gap between quantum mechanics and general relativity, reshaping our understanding of the universe itself. Now turning to the 10th of our 50 space mysteries, we delve into the puzzling case of the Pioneer Anomaly. This mystery revolves around the unexpected deceleration of the Pioneer 10 and Pioneer 11 spacecraft as they journeyed through the outer reaches of our solar system. Launched in the early 1970s, these spacecraft were designed to explore the outer planets and beyond, but as they ventured farther from the Sun, scientists noticed something strange. Both spacecraft were slowing down slightly more than predicted by the known laws of physics. This unexplained deceleration, though tiny, was consistent and defied all expectations. It became known as the Pioneer Anomaly, and for decades it baffled researchers. the discrepancy was equivalent to a force about 10 billion times weaker than gravity on Earth acting on the spacecraft. While it might seem insignificant, such a deviation could have profound implications for our understanding of physics. One of the leading explanations for the anomaly involves thermal radiation. The spacecraft were powered by radioisotope thermoelectric generators, which produced heat as a byproduct. Some scientists proposed that this heat, radiating unevenly from the spacecraft, could have created a tiny but measurable thrust, causing the deceleration. However, detailed analyses of the spacecraft's design and thermal properties have not fully accounted for the observed effect, leaving this theory incomplete. Another possibility is that the Pioneer Anomaly hints at new physics beyond our current understanding. Some researchers have speculated that it could be evidence of modifications to Einstein's theory of general relativity, or even the influence of dark matter or dark energy. These ideas remain speculative, but they highlight how even the smallest anomalies can challenge our fundamental assumptions about the universe. Despite extensive investigations, the Pioneer Anomaly remains unresolved. It serves as a reminder that even in the vastness of space, the smallest details can hold the keys to unlocking profound mysteries. As we continue to explore the cosmos, anomalies like this one push us to refine our theories and deepen our understanding of the forces that shape our universe. Now turning to the 11th of our 50 space mysteries, we explore the enigmatic origins of our moon. For centuries, the moon has been a source of fascination and wonder, but how it came to be remains one of the most enduring puzzles in planetary science. The leading theory, known as the giant impact hypothesis, suggests that the moon formed from the debris of a colossal collision between a young Earth and a Mars-sized protoplanet, often referred to as Theia, around 4.5 billion years ago. This cataclysmic event would have ejected vast amounts of material into orbit around Earth, which eventually coalesced to form the moon. While the giant impact hypothesis is widely accepted, it is not without its challenges. For instance, simulations of such an impact struggle to fully explain the moon's current composition, which is strikingly similar to Earth's mantle. If the moon formed primarily from Theia's debris, its composition should differ more significantly from Earth. This has led some scientists to propose alternative theories, such as the idea that multiple smaller impacts, rather than a single giant collision, contributed to the moon's formation. Others have suggested that Earth was spinning much faster at the time of the impact, which could have altered the dynamics of the collision and the resulting debris. Another mystery lies in the moon's isotopic composition. Isotopes are variants of elements with different numbers of neutrons, and their ratios can act like fingerprints, revealing the origins of planetary materials. Surprisingly, the isotopic signatures of Earth and the Moon are nearly identical, which is difficult to reconcile with the giant impact hypothesis. Some researchers have proposed that Theia might have had a composition very similar to Earth's, but this raises further questions about how such a scenario could occur. Despite decades of research, gaps in our understanding persist. For example, we still do not know the exact size of Theia, the precise angle and speed of the collision, or how the ejected material settled into a stable orbit. These uncertainties highlight the complexity of reconstructing events that occurred billions of years ago, and they remind us that even our closest celestial neighbor holds secrets yet to be uncovered. The Moon's origin is not just a scientific curiosity. It has profound implications for understanding the early solar system and the formation of terrestrial planets. As we continue to study lunar rocks, conduct advanced simulations, and plan future missions to the Moon, we inch closer to unraveling this cosmic mystery. Each new discovery brings us one step closer to understanding not only how our Moon came to be, but also how Earth and other rocky planets evolved in the dynamic environment of the early solar system. Now turning to the 12th of our 50 space mysteries, we delve into the Tunguska event, one of the most powerful and mysterious explosions in recorded history. On June 30th, 1908, a massive explosion rocked the remote forests of Siberia near the Tunguska River. The blast flattened an estimated 2,000 square kilometers of forest, snapping trees like matchsticks and sending shockwaves that were felt hundreds of kilometers away. Despite its immense power, the event left no crater, deepening the mystery of what exactly caused it. The leading theory suggests that the explosion was caused by a meteoroid or comet entering Earth's atmosphere and disintegrating before it could hit the ground. The resulting airburst would have released energy equivalent to 10 to 15 megatons of TNT, hundreds of times more powerful than the atomic bomb dropped on Hiroshima. However, no fragments of the object have ever been found, leaving scientists to rely on simulations and comparisons to other airburst events, like the Chelyabinsk meteor in 2013. Some researchers have proposed more exotic explanations. One theory suggests that the Tunguska event was caused by a small black hole passing through Earth. While this idea is intriguing, there is no evidence to support it, and it remains highly speculative. Another hypothesis involves antimatter, suggesting that a chunk of antimatter collided with Earth, annihilating itself and releasing a tremendous amount of energy. However, this theory also lacks concrete evidence and is considered unlikely by most scientists. The lack of a crater and the absence of physical debris have made the Tunguska event a puzzle that continues to captivate researchers. Some have even speculated that the explosion could have been caused by a natural gas explosion or a volcanic event, though these theories struggle to explain the scale and characteristics of the blast. The Tunguska event serves as a stark reminder of the potential dangers posed by near-Earth objects. It has spurred efforts to track asteroids and comets that could pose a threat to our planet, as well as initiatives to develop strategies for planetary defense. While the true cause of the Tunguska explosion remains uncertain, it stands as a testament to the unpredictable and awe-inspiring forces at work in our universe. As we continue to study this enigmatic event, we gain not only a deeper understanding of our planet's history, but also valuable insights into the cosmic hazards that could shape our future. Now turning to the 13th of our 50 space mysteries, we explore the cosmic microwave background cold spot, a puzzling anomaly in the afterglow of the Big Bang. The cosmic microwave background, or CMB, is the oldest light in the universe, a faint glow left over from the moment the universe became transparent, about 380,000 years after the Big Bang. This radiation is remarkably uniform, but there's one region that stands out as unusually cold, a cold spot that defies expectations. The cold spot, located in the constellation Eridanus, is about 70 microkelvin colder than the average temperature of the CMB. At first glance, this might not seem significant, but in the context of the universe's early history, it's a glaring anomaly. Scientists have proposed several theories to explain this cold spot, each more intriguing than the last. One leading theory suggests that the cold spot could be the result of a supervoid, a vast, nearly empty region of space where matter is sparsely distributed. As light travels through such a void, it loses energy, a phenomenon known as the integrated Sachs-Wolfe effect. This could explain why the cold spot appears colder than its surroundings. However, recent observations have found that the supervoid in this region isn't large enough to fully account for the temperature drop, leaving this explanation incomplete. Another, more speculative theory involves the idea of parallel universes. Some researchers propose that the cold spot could be evidence of a collision between our universe and another bubble universe during the early moments of cosmic inflation. While this idea is fascinating, it remains highly theoretical and lacks direct evidence. Critics argue that the cold spot could simply be a statistical fluke, a rare but natural variation in the CMB. There's also the possibility that the cold spot is the result of errors in data interpretation or instrumental effects. The CMB is measured with incredible precision, but even the most advanced instruments can introduce subtle biases or artifacts. Scientists continue to refine their measurements and analysis techniques to rule out these possibilities. The cosmic microwave background cold spot remains one of the most tantalizing mysteries in cosmology. Whether it's a sign of a supervoid, a glimpse of a parallel universe, or simply a quirk of nature, it challenges our understanding of the universe's origins and structure. As we probe deeper into this enigma, we may uncover new insights into the fundamental nature of reality itself. Now turning to the 14th of our 50 space mysteries, we delve into the missing baryon problem, a cosmic puzzle that has left scientists scratching their heads. When we look at the universe, we expect to find a certain amount of ordinary matter, or baryons, the protons and neutrons that make up stars, planets, and even us. But here's the catch. Observations show that about half of this expected matter is missing. So, where did it go? The missing baryons are thought to be hiding in the vast, diffuse regions of space between galaxies in a form known as the warm-hot intergalactic medium, or WIM. This elusive material is incredibly difficult to detect because it spreads so thinly and doesn't emit much light. However, recent advancements in technology have given us new ways to search for it. By studying the absorption of light from distant quasars as it passes through these intergalactic regions, scientists have begun to uncover faint traces of the missing matter. Another possibility is that the missing baryons are tied up in massive cosmic structures like filaments, which connect galaxies in a vast web-like network. These filaments, made of hot gas, are thought to contain a significant portion of the universe's ordinary matter. Yet, even with this theory, the exact amount and distribution of these baryons remain unclear. Some researchers have also suggested that the missing matter could be hiding in the form of dark baryons, ordinary matter, that's simply too faint or too cold to detect with current instruments. This idea adds another layer of complexity to the mystery, as it challenges our understanding of how matter behaves on cosmic scales. The missing baryon problem is more than just a cosmic accounting error. It's a fundamental question about the structure and composition of the universe. Solving it could help us better understand how galaxies form, how the cosmic web evolves, and even how the universe itself came to be. As we continue to refine our observations and develop new tools, we may finally uncover the secrets of these elusive baryons, shedding light on one of the most enduring mysteries of the cosmos. Now turning to the 15th of our 50 space mysteries, we encounter a phenomenon so puzzling that it's been dubbed the axis of evil. This mystery revolves around the cosmic microwave background radiation, or CMB, which is the faint afterglow of the Big Bang. The CMB is one of the most important pieces of evidence supporting the Big Bang theory, as it provides a snapshot of the universe when it was just 380,000 years old. But here's where things get strange. The CMB shows an unexpected alignment with the plane of our solar system, a discovery that has left scientists both intrigued and baffled. This alignment, known as the axis of evil, suggests that the universe might not be as uniform as we once thought. According to the Big Bang theory, the early universe should have been isotropic, meaning it should look the same in all directions. However, the CMB reveals patterns that seem to align with the orientation of our solar system, which shouldn't happen if the universe is truly random and uniform. This unexpected correlation has raised questions about whether there's something special about our place in the cosmos, or if there's a flaw in our understanding of the Big Bang itself. One possibility is that the axis of evil is a result of some unknown local effect, such as contamination from our own galaxy or even the solar system. However, extensive studies have ruled out most of these explanations, leaving the mystery unsolved. Another theory suggests that the alignment could be evidence of a larger structure or anisotropy in the universe, challenging the fundamental assumption that the cosmos is the same in all directions. If true, this would have profound implications for cosmology. potentially requiring us to rethink the very foundations of our understanding of the universe. The axis of evil also raises questions about the nature of dark energy and dark matter, as these mysterious components make up the majority of the universe's content. Could their distribution or behavior be influencing the CMB in ways we don't yet understand? Or is there some deeper, yet to be discovered principle at work? Whatever the answer, the axis of evil serves as a reminder that even our most well-established theories can be challenged by new observations. As we continue to study the CMB with increasingly sensitive instruments, we may one day uncover the truth behind this cosmic anomaly. Until then, the axis of evil remains one of the most intriguing and controversial mysteries in modern cosmology, pushing us to question what we think we know about the universe and our place within it. Now turning to the 16th of our 50 space mysteries, we venture into one of the most perplexing voids in the universe, the boötes void. This enormous region of space, located in the constellation of Boötes, is a cosmic desert unlike anything else we've observed. Stretching across an astonishing 330 million light-years, the Boötes void is so vast that it could fit thousands of galaxies, yet it contains only a handful. This extreme emptiness challenges our understanding of how the universe is structured and raises questions about what could have caused such a colossal void to form. The Boötes void defies the standard model of cosmology, which predicts that matter should be distributed relatively evenly across the universe. Instead, this region is a glaring anomaly, a place where galaxies are almost entirely absent. Scientists have proposed several theories to explain its existence. One possibility is that the void formed as a result of smaller voids merging over billions of years, creating a single, massive, empty region. Another theory suggests that the Boötes void could be the result of an early universe phenomenon, such as a quantum fluctuation that left this area devoid of matter during the Big Bang. However, neither of these explanations fully accounts for the sheer scale of the void or its near-total emptiness. Some researchers have even speculated that the Boötes void could be evidence of something far more exotic, such as the influence of dark energy or the remnants of a collision between our universe and another in a hypothetical multiverse. While these ideas remain speculative, they highlight just how little we understand about the forces that shape the cosmos. The Boötes void also raises questions about the nature of cosmic structure. If such enormous voids exist, what does that mean for the large-scale distribution of matter in the universe? Could there be other voids, even larger and more mysterious, waiting to be discovered? And how do these voids affect the evolution of galaxies and the overall fate of the universe? These are questions that astronomers and cosmologists are still grappling with as they continue to map the universe in greater detail. As we peer deeper into the cosmos, the Boötes void stands as a stark reminder of how much we have yet to learn. Its existence challenges our assumptions and pushes us to rethink the very fabric of the universe. Whether it's a cosmic accident, a sign of deeper physics, or something entirely beyond our current understanding, the Boötes void remains one of the most enigmatic features of the cosmos, inviting us to explore further and uncover its secrets. Now turning to the 17th of our 50 space mysteries, we encounter a celestial object that stands out for its striking appearance and puzzling origins, the Red Rectangle Nebula. Located about 2,300 light-years from Earth in the constellation Monoceros, this nebula is unlike any other in the cosmos. Its name comes from its distinct geometric shape and vivid red hue, which make it one of the most visually intriguing objects in the night sky. The Red Rectangle Nebula's unique structure is thought to be the result of a binary star system at its center. These two stars, locked in a close orbit, are believed to be the driving force behind the nebula's formation. As the stars interact, they eject material into space, creating a series of concentric rings and a rectangular-like shape. This process, known as bipolar outflow, is not uncommon in binary systems, but the Red Rectangle Nebula takes it to an entirely new level of complexity and beauty. What makes this nebula even more mysterious is its intense red color. This hue is caused by a phenomenon called fluorescence, where ultraviolet light from the central stars excites hydrogen molecules in the surrounding gas, causing them to emit red light. However, the exact mechanisms behind the nebula's precise geometric structure and the distribution of its glowing material remain unclear. Scientists are still trying to understand how such a perfect, almost artificial-looking shape could emerge from the chaotic processes of stellar evolution. Adding to the intrigue, the Red Rectangle Nebula is also rich in complex organic molecules, including hydrocarbons. These compounds are some of the building blocks of life, raising questions about whether similar processes could occur elsewhere in the universe, potentially contributing to the origins of life. Could this nebula be a cosmic laboratory where the ingredients for life are being mixed and tested? While we don't yet have the answers, the Red Rectangle Nebula offers a fascinating glimpse into the intricate and often mysterious workings of the cosmos. As we continue to study this remarkable object, it challenges our understanding of how stars and their surrounding environments evolve. The Red Rectangle Nebula is a testament to the beauty and complexity of the universe, reminding us that even the most familiar processes can produce results that defy our expectations. Its secrets remain locked within its glowing red walls, waiting for future observations and discoveries to unravel them. Now turning to the 18th of our 50 space mysteries, we delve into the enigmatic Eridanus supervoid, a vast and nearly empty region of space that has left scientists scratching their heads. Located in the constellation Eridanus, this supervoid spans an astonishing 1 billion light-years across, making it one of the largest structures ever discovered in the universe. But what makes it truly fascinating is its potential connection to another cosmic mystery, the cold spot in the cosmic microwave background radiation. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, and it provides a snapshot of the early universe. Within this radiation, there's a peculiar cold spot, a region that's significantly cooler than its surroundings. For years, scientists have debated what could cause such a temperature anomaly. One leading theory points to the Eridanus supervoid. The idea is that this enormous void, with its lack of matter and energy, could be causing light from the CMB to lose energy as it passes through, creating the observed cold spot. This phenomenon, known as the integrated Sachs-Wolfe effect, suggests that the supervoid's gravitational influence might be stretching the light waves, making them appear cooler. However, the connection between the Eridanus supervoid and the CMB cold spot is far from settled. Some researchers argue that the supervoid isn't large or empty enough to fully explain the cold spot's extreme temperature drop. Others propose alternative explanations, such as the possibility of a collision between our universe and another parallel universe, or even a flaw in our understanding of cosmology itself. The debate continues, and the Eridanus supervoid remains a tantalizing puzzle. Beyond its connection to the CMB cold spot, the Eridanus supervoid challenges our understanding of the universe's large-scale structure. According to the standard model of cosmology, matter should be distributed relatively evenly across the cosmos. Yet, voids like this one defy that expectation, raising questions about how such vast, empty regions form and what they mean for the overall structure of the universe. Could they be the result of cosmic inflation, or do they hint at new physics that we have yet to discover? As we explore the Eridanus supervoid, it serves as a reminder of how much we still have to learn about the cosmos. Its sheer size and emptiness, combined with its potential link to the CMB cold spot, make it a key piece in the puzzle of understanding the universe's origins and evolution. While the answers remain elusive, the Eridanus supervoid continues to inspire curiosity and drive scientific inquiry, pushing us to rethink our assumptions and explore new frontiers in cosmology. Now turning to the 19th of our 50 space mysteries, we explore the fascinating and somewhat unsettling phenomenon of cannibal galaxies. These cosmic giants, often found at the centers of galaxy clusters, have a voracious appetite for their smaller neighbors. But what exactly happens when a galaxy consumes another, and how do these interactions shape the evolution of galaxies over billions of years? Galactic cannibalism occurs when a larger galaxy, typically a massive elliptical galaxy, gravitationally pulls in and absorbs a smaller galaxy. This process is driven by the immense gravitational forces exerted by the larger galaxy, which can strip away stars, gas, and dust from the smaller one. Over time, the smaller galaxy is completely assimilated, its material becoming part of the larger galaxy's structure. This might sound like a violent process, but it's actually a slow and gradual one, taking place over hundreds of millions or even billions of years. One of the most famous examples of a cannibal galaxy is Messier 87, or M87, located in the Virgo cluster. This supergiant elliptical galaxy is thought to have consumed dozens of smaller galaxies over its lifetime. Evidence of this can be seen in the form of stellar streams, long trails of stars that were once part of smaller galaxies, but are now being pulled into M87's gravitational embrace. These streams act as cosmic breadcrumbs, revealing the history of galactic mergers and the ongoing process of galaxy growth. But why does this matter? Galactic cannibalism plays a crucial role in shaping the universe as we see it today. When galaxies merge, they don't just grow in size, they also trigger new star formation. The influx of gas and dust from the smaller galaxy can ignite bursts of star formation in the larger one, leading to the creation of new stars and planetary systems. At the same time, these interactions can also feed supermassive black holes at the centers of galaxies, causing them to become active and emit powerful jets of energy. However, the process isn't fully understood. For instance, why do some galaxies become cannibals while others remain relatively isolated? What determines the outcome of these interactions, whether they lead to a burst of star formation or the quenching of star formation altogether? And how do these mergers influence the overall structure and dynamics of galaxy clusters? These are some of the questions that continue to puzzle astronomers. The study of cannibal galaxies also provides insights into the hierarchical model of galaxy formation, which suggests that large galaxies grow by merging with smaller ones. This model has been largely successful in explaining the observed distribution of galaxies in the universe, but there are still gaps in our understanding. For example, simulations of galaxy mergers often struggle to reproduce the exact properties of real galaxies, suggesting that there may be additional factors at play, such as dark matter or feedback from supermassive black holes. As we delve deeper into the mysteries of cannibal galaxies, we gain a better understanding of how galaxies evolve and interact over cosmic time. These interactions are not just destructive, they are also creative, driving the formation of new stars, planets, and even entire galactic structures. While the process may seem chaotic, it is a fundamental part of the universe's story, shaping the cosmos into the intricate and beautiful tapestry we observe today. The study of cannibal galaxies reminds us that the universe is a dynamic and ever-changing place, full of surprises waiting to be uncovered. Now turning to the 20th of our 50 space mysteries, we shift our gaze to the heart of our own galaxy, the Milky Way, where an enigmatic phenomenon known as the galactic center excess has left scientists scratching their heads. At the very core of our galaxy, astronomers have detected an unusual amount of gamma-ray radiation, a type of high-energy light that shouldn't be there based on our current understanding of the Milky Way's structure and behavior. This mysterious glow, concentrated around the galactic center, has sparked a flurry of theories ranging from the annihilation of dark matter to the activity of dense, spinning stellar remnants known as pulsars. The galactic center excess was first discovered by NASA's Fermi Gamma Ray Space Telescope, which has been mapping the gamma-ray sky since its launch in 2008. The excess appears as a diffuse, spherical glow of gamma rays emanating from the region surrounding the supermassive black hole at the center of the Milky Way, known as Sagittarius, a star. While some gamma-ray emissions are expected from cosmic rays interacting with gas and dust, the intensity and distribution of this excess radiation don't match any known astrophysical processes. This has led scientists to consider more exotic explanations. One of the most intriguing possibilities is that the excess gamma rays are being produced by dark matter particles annihilating each other. According to this theory, dark matter, the invisible substance that makes up about 85% of the universe's mass, could be concentrated in the galactic center. If dark matter particles collide and annihilate, they could produce gamma rays as a byproduct. This idea has captivated researchers because it could provide the first direct evidence of dark matter's existence. However, despite extensive modeling and analysis, no definitive proof has been found, leaving this theory tantalizing but unconfirmed. Another leading explanation involves pulsars rapidly rotating neutron stars that emit beams of radiation, including gamma rays. These dense stellar remnants are scattered throughout the galaxy, and their combined emissions could potentially account for the excess gamma rays observed at the galactic center. Some scientists argue that a population of faint, unresolved pulsars, too dim to be detected individually, could be responsible for the glow. This theory is supported by the fact that pulsars are known to produce gamma rays, and their distribution could align with the observed excess. However, the exact number and nature of these pulsars remain uncertain, leaving room for debate. The mystery of the galactic center excess highlights the challenges of studying the dense and chaotic environment at the heart of our galaxy. The region is filled with gas, dust, and a multitude of stars, making it difficult to isolate the source of the gamma rays. Additionally, the supermassive black hole at the center of the Milky Way adds another layer of complexity, as its immense gravitational pull and energetic outbursts could influence the surrounding environment in ways we don't yet fully understand. As astronomers continue to investigate this cosmic puzzle, they are using increasingly sophisticated tools and techniques. New observations from gamma-ray telescopes, combined with advanced computer simulations, are helping to narrow down the possible explanations. Whether the excess is ultimately linked to dark matter, pulsars, or some other unknown phenomenon, solving this mystery could provide profound insights into the nature of our galaxy and the universe as a whole. The galactic center excess serves as a reminder that even in our own cosmic backyard, there are still secrets waiting to be uncovered. It challenges us to rethink our assumptions and pushes the boundaries of our understanding, proving once again that the universe is far more complex and mysterious than we often imagine. As we continue to explore this enigma, we move one step closer to unraveling the deeper truths of the cosmos. Now turning to the 21st of our 50 space mysteries, we venture to the outer reaches of our solar system, where an abrupt and puzzling boundary known as the Kuiper Cliff awaits. Beyond the Kuiper Belt, a vast region of icy bodies and dwarf planets like Pluto, there lies a sudden and dramatic drop-off in the number of objects. This unexpected boundary, located roughly 4.5 billion miles from the Sun, has left scientists questioning what could cause such a sharp decline in the population of celestial bodies. The Kuiper Belt itself is a treasure trove of ancient remnants from the early solar system, offering clues about how planets formed and evolved. However, as astronomers map the distribution of objects in this region, they've noticed that beyond a certain distance, the number of objects drops off almost entirely. This abrupt edge, known as the Kuiper Cliff, defies expectations as models of the solar system's formation suggest that the Kuiper Belt should gradually thin out rather than end so abruptly. One of the most compelling theories to explain the Kuiper Cliff involves the possibility of a hidden planet lurking in the distant reaches of our solar system. This hypothetical world, often referred to as Planet 9, could have a gravitational influence strong enough to clear out objects beyond a certain distance. According to this idea, Planet 9's orbit would be highly elliptical, taking it far beyond the Kuiper belt and periodically sweeping through the outer solar system. Its gravitational pull could have either ejected objects from the region or pushed them into unstable orbits, creating the observed drop-off. While no direct evidence of Planet 9 has been found yet, its existence remains a tantalizing possibility that could solve multiple solar system mysteries. Another theory suggests that the Kuiper cliff might be the result of a massive collision in the early solar system. If a large object, perhaps even a rogue planet or a passing star, once disrupted the outer regions, it could have scattered or destroyed many of the objects beyond the Kuiper belt. This catastrophic event would have left behind a clear boundary, marking the edge of the surviving population of icy bodies. While this idea is speculative, it highlights the dynamic and often violent history of our solar system's formation. The Kuiper cliff also raises questions about the conditions in the outer solar system billions of years ago. Some scientists propose that the drop-off could be linked to the way material was distributed during the solar system's infancy. If the protoplanetary disk, the swirling cloud of gas and dust from which the planets formed, had a sharp edge, it could explain why objects are scarce beyond a certain distance. Alternatively, interactions with the Sun's early environment, such as radiation or stellar winds, might have played a role in shaping the Kuiper belt's outer boundary. As astronomers continue to study the Kuiper cliff, they are using advanced telescopes and computer simulations to probe this distant frontier. Missions like New Horizons, which flew past Pluto in 2015, have provided valuable data about the Kuiper belt and its inhabitants. Future observations, particularly those focused on the outer solar system, could shed light on whether the Kuiper cliff is the result of a hidden planet, a past collision, or some other cosmic process. The mystery of the Kuiper cliff reminds us that even in our own solar system, there are still unanswered questions waiting to be explored. It challenges our understanding of how planetary systems form and evolve, and it underscores the importance of continued exploration. As we peer into the icy depths of the Kuiper belt and beyond, we may uncover clues that reshape our knowledge of the solar system's history and its hidden secrets. Now turning to the 22nd of our 50 space mysteries, we delve into the intriguing hypothesis of a hidden ninth planet in our solar system. Known as Planet 9, this hypothetical world has captured the imagination of astronomers and space enthusiasts alike. The idea of a distant, undiscovered planet stems from peculiar gravitational patterns observed in the orbits of objects in the outer solar system, particularly in the Kuiper belt. These objects exhibit unusual clustering, suggesting the presence of a massive body influencing their paths. The evidence for Planet 9 lies in the way these distant objects move. Their orbits appear to be tilted and aligned in a way that cannot be easily explained by the known planets alone. Scientists have calculated that a planet roughly 10 times the mass of Earth, with an orbit stretching far beyond Neptune, could account for these anomalies. This hypothetical planet would take between 10,000 and 20,000 years to complete a single orbit around the Sun, making it a true outlier in our solar system. The potential size and characteristics of Planet 9 are equally fascinating. If it exists, it could be a super-Earth, a type of planet larger than Earth but smaller than ice giants like Uranus and Neptune. Its surface might be icy with a thick atmosphere, or it could resemble a mini Neptune. However, its extreme distance from the Sun makes it incredibly challenging to detect. The faint light it reflects will be overwhelmed by the brightness of nearby stars, and its slow movement across the sky would make it difficult to distinguish from background objects. Detecting Planet 9 poses significant challenges. Traditional methods of observing planets, such as direct imaging, are complicated by its immense distance and the vast area of sky that must be searched. Astronomers are relying on indirect evidence such as its gravitational effects on other objects and advanced telescopes like the Vera-C Rubin Observatory, which is set to begin operations in the coming years. This observatory's wide-field surveys could potentially spot Planet 9 or provide further clues about its existence. The search for Planet 9 is not just about finding another planet, it's about understanding the dynamics of our solar system. If confirmed, it would reshape our knowledge of how planetary systems form and evolve, offering insights into the early history of our cosmic neighborhood. It could also explain other mysteries such as the Kuiper cliff and the unusual orbits of distant objects. As the hunt for Planet 9 continues, it serves as a reminder of how much we still have to learn about our own solar system. Whether it's a massive, icy world lurking in the shadows or a cosmic illusion created by other forces, the mystery of Planet 9 challenges us to push the boundaries of exploration and discovery. With each new observation and simulation, we move closer to uncovering the truth about this enigmatic potential planet and its place in the grand tapestry of the cosmos. Now turning to the 23rd of our 50 space mysteries, we shift our focus to the enigmatic presence of methane on Mars. This gas, often associated with life on Earth, has been detected intermittently in the Martian atmosphere, sparking intense debate and curiosity among scientists. The mystery lies not just in its detection, but in the fact that methane on Mars appears and disappears in ways that defy easy explanation. Could this be a sign of microbial life beneath the surface, or is there a geological process at work that we don't yet understand? Methane is a molecule that, on Earth, is primarily produced by living organisms, though it can also be generated through geological processes like volcanic activity or the interaction of water with certain rocks. On Mars, the detection of methane has been sporadic, with some instruments, like the Curiosity rover, picking up traces of it, while others, like the European Space Agency's Trace Gas Orbiter, have found little to no evidence. This inconsistency has made it difficult to pinpoint the source of the gas, adding another layer of intrigue to the mystery. One of the leading theories is that methane on Mars could be produced by microbial life forms living deep underground, where conditions might be more hospitable than on the harsh surface. These microbes, if they exist, could be generating methane as a byproduct of their metabolism, much like some bacteria do on Earth. However, proving this theory is incredibly challenging. The Martian surface is bombarded by ultraviolet radiation and cosmic rays, which can break down methane molecules quickly. This means that any methane detected must have been released relatively recently, suggesting an active source. On the other hand, geological processes could also explain the presence of methane. Mars has a history of volcanic activity, and while no active volcanoes have been observed, it's possible that subsurface heat could be driving chemical reactions that produce methane. Another possibility is that methane is being released from ancient reservoirs trapped in ice or rock, slowly seeping out over time. Distinguishing between these possibilities requires more data and advanced instruments capable of analyzing the Martian environment in greater detail. The challenges of confirming the source of methane on Mars are significant. The planet's thin atmosphere and extreme conditions make it difficult to conduct precise measurements. Additionally, the intermittent nature of the methane detections means that scientists often have to rely on limited data, making it hard to draw definitive conclusions. Future missions like NASA's Mars Sample Return Program aim to bring Martian soil and rock samples back to Earth for more detailed analysis, which could provide crucial insights into this mystery. The implications of solving the methane mystery are profound. If the gas is indeed produced by microbial life, it would be the first definitive evidence of life beyond Earth, revolutionizing our understanding of biology and our place in the universe. Even if the source turns out to be geological, it would still provide valuable information about the planet's history and potential habitability. As we continue to explore Mars, the search for answers about its methane remains a tantalizing puzzle, one that could unlock secrets about the red planet and the possibility of life elsewhere in the cosmos. Now turning to the 24th of our 50 space mysteries, we venture to Jupiter's moon Europa, a world that has captivated scientists with the tantalizing possibility of a vast, hidden ocean beneath its icy surface. Europa, one of Jupiter's largest moons, is covered in a thick layer of ice, but beneath this frozen shell lies what many believe to be a global ocean of liquid water. This discovery has made Europa one of the most promising places in our solar system to search for extraterrestrial life. The evidence for Europa's subsurface ocean comes from multiple sources. Observations from spacecraft like NASA's Galileo mission have revealed that Europa's surface is relatively smooth and young, with few craters, suggesting that it is constantly being reshaped. This points to the presence of a liquid layer beneath the ice, which could be moving and shifting the surface over time. Additionally, measurements of Europa's magnetic field indicate the presence of a conductive layer, likely a salty ocean beneath the ice. These findings have led scientists to conclude that Europa's ocean could be twice as large as all of Earth's oceans combined. What makes this ocean so intriguing is the possibility that it could harbor life. On Earth, life thrives in some of the most extreme environments, from deep-sea hydrothermal vents to subglacial lakes in Antarctica. Europa's ocean, shielded from the harsh radiation of space by its icy crust, could provide a stable environment where microbial life might exist. The presence of essential elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, combined with the potential for hydrothermal activity on Europa's ocean floor, creates a recipe for habitability that scientists are eager to explore. However, exploring Europa's ocean presents significant challenges. The moon's icy shell is estimated to be several kilometers thick, making it difficult to access the ocean directly. Scientists have proposed various methods to overcome this obstacle, from drilling through the ice to using robotic probes that could melt their way down. One of the most promising approaches is the use of ice-penetrating radar and other instruments to study the ocean indirectly, mapping its depth and composition from orbit. Future missions like NASA Europa Clipper aim to gather more data about Europa's ocean and its potential to support life. Scheduled to launch in the coming years, the Europa Clipper will conduct detailed reconnaissance of the moon's ice shell and subsurface ocean, searching for signs of recent geological activity and plumes of water vapor that might erupt from the surface. These plumes, if detected, could provide a way to sample Europa's ocean without needing to drill through the ice, offering a glimpse into the chemistry and potential habitability of this hidden world. The implications of finding life on Europa would be nothing short of revolutionary. It would not only confirm that life can exist beyond Earth, but also open up new possibilities for where and how life might thrive in the universe. Even if no life is found, the exploration of Europa's ocean would deepen our understanding of the processes that shape icy moons and the potential for habitable environments in our solar system and beyond. As we continue to study Europa, the mysteries of its hidden ocean remain a beacon of hope and curiosity, drawing us closer to answering one of humanity's most profound questions: are we alone in the cosmos? Now turning to the 25th of our 50 space mysteries, we shift our gaze to Saturn's moon Enceladus, a small but incredibly active world that has stunned scientists with its spectacular geysers of water vapor. These plumes erupting from the moon's south pole are not just a breathtaking sight, they are a window into what might lie beneath Enceladus' icy surface. Like Europa, Enceladus is believed to harbor a subsurface ocean, and its plumes offer a tantalizing opportunity to study this hidden world without even needing to land on the surface. The discovery of Enceladus plumes came as a surprise during NASA's Cassini mission, which orbited Saturn from 2004 to 2017. Cassini's instruments detected towering jets of water vapor, ice particles, and organic molecules shooting hundreds of kilometers into space from fractures in the moon's icy crust, known as tiger stripes. These plumes are not only visually stunning but also scientifically significant, as they provide direct evidence of a liquid water reservoir beneath the ice. Analysis of the material ejected by the plumes revealed the presence of salts, silica, and complex organic compounds, ingredients that are essential for life as we know it. What makes Enceladus particularly intriguing is the potential connection between its plumes and a subsurface ocean. Scientists believe that the plumes are fed by this ocean, which is kept liquid by tidal forces generated by Saturn's gravity. As Enceladus orbits Saturn, the planet's immense gravitational pull stretches and compresses the moon, generating heat that prevents the ocean from freezing. This process, known as tidal heating, could also create hydrothermal vents on the ocean floor, similar to those found in Earth's deep oceans. On Earth, such vents are teeming with life, raising the possibility that Enceladus Ocean might also host microbial organisms. The plumes themselves offer a unique opportunity to study this hidden ocean. Cassini flew through the plumes multiple times, sampling their composition and providing valuable data about the ocean's chemistry. The presence of molecular hydrogen in the plumes, detected during one of Cassini's final flybys, was particularly exciting. On Earth, hydrogen is a key energy source for microbes living near hydrothermal vents, suggesting that Enceladus Ocean might have the necessary conditions to support life. Future missions to Enceladus could take this exploration even further. Proposals include sending spacecraft equipped with advanced instruments to analyze the plumes in greater detail, or even landing on the moon's surface to study the tiger stripes up close. Some scientists have even suggested the possibility of a mission that could collect samples from the plumes and return them to Earth for analysis. Such a mission could provide definitive answers about the habitability of Enceladus Ocean and whether life exists there. The implications of finding life on Enceladus would be profound. Like Europa, Enceladus represents a new frontier in the search for extraterrestrial life, challenging our understanding of where life can exist in the universe. Even if no life is found, the study of Enceladus plumes and ocean would deepen our knowledge of icy moons and the processes that sustain liquid water in the outer solar system. As we continue to explore this enigmatic moon, its plumes remain a symbol of the mysteries that await us in the cosmos, reminding us that even the smallest worlds can hold the greatest secrets. Now turning to the 26th of our 50 space mysteries, we journey to Saturn's largest moon, Titan, a world unlike any other in our solar system. Titan is shrouded in a thick, hazy atmosphere, but beneath its orange clouds lies a landscape that is both alien and eerily familiar. What makes Titan truly extraordinary are its vast lakes and seas, not of water but of liquid methane and ethane. These hydrocarbon lakes make Titan the only place in the solar system, other than Earth, known to have stable bodies of liquid on its surface. The discovery of Titan's lakes came as a result of data collected by NASA Cassini mission, which revealed a world of rivers, deltas, and even rain, all driven by methane rather than water. Titan's surface temperature hovers around -180 degrees Celsius, far too cold for liquid water to exist. Instead, methane and ethane take on the roles that water plays on Earth, evaporating, condensing, and falling as rain to carve out valleys and fill vast basins. The largest of these, Kraken Mare, is a sea of liquid hydrocarbons that stretches over 1,000 kilometers across, making it larger than Earth's Caspian Sea. What makes Titan's chemistry so fascinating is its potential to mimic the conditions of early Earth, albeit in a much colder environment. Methane and ethane are organic molecules, and their presence in such abundance raises intriguing questions about the possibility of exotic life forms. While life as we know it requires liquid water, some scientists speculate that Titan's methane-based chemistry could support a completely different kind of biology. Hypothetical life forms on Titan might use liquid methane as a solvent instead of water, and their metabolism could rely on chemical reactions involving hydrocarbons rather than oxygen. Titan's atmosphere adds another layer of mystery. It is rich in nitrogen like Earth's, but also contains complex organic molecules that form in the upper atmosphere and rain down to the surface. These molecules, known as tholins, are thought to be the building blocks of more complex chemistry, potentially even probiotic compounds. Some researchers believe that Titan's lakes and atmosphere could be a laboratory for studying the chemical processes that might lead to life under very different conditions than those on Earth. The exploration of Titan has only just begun. In 2005, the European Space Agency's Huygens probe, carried by Cassini, became the first and only spacecraft to land on Titan's surface. It sent back images of a landscape strewn with rounded pebbles, likely shaped by flowing methane, and revealed a world that felt both alien and strangely Earth-like. Future missions such as NASA's Dragonfly aim to take this exploration to the next level. Dragonfly, set to launch in the late 2020s, is a rotorcraft designed to fly across Titan's surface, sampling its chemistry and searching for signs of probiotic processes or even life. The implications of Titan's lakes and chemistry are profound. They challenge our understanding of where and how life might arise, expanding the possibilities beyond the traditional, habitable zone of liquid water. Titan reminds us that life, if it exists elsewhere in the universe, might not look anything like what we know on Earth. As we continue to study this enigmatic moon, its methane lakes stand as a testament to the diversity and complexity of worlds in our solar system, inviting us to rethink what it means to be alive. Now turning to the 27th of our 50 space mysteries, we shift our gaze from the frigid lakes of Titan to the scorching atmosphere of Venus, Earth's so-called evil twin. In 2020, a startling discovery sent shockwaves through the scientific community: the detection of phosphine gas in Venus's upper atmosphere. Phosphine, a molecule made up of one phosphorus atom and 3 hydrogen atoms, is considered a potential biosignature, a chemical that could indicate the presence of life. On Earth, phosphine is primarily produced by microbial life in oxygen-free environments, such as swamps or the guts of certain animals. Its presence on Venus raised the tantalizing possibility that microbial life might exist in the planet's clouds despite its hellish surface conditions. The discovery was made using the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter Array in Chile. These instruments detected the spectral signature of phosphine at altitudes between 50 and 60 kilometers above Venus's surface, where temperatures and pressures are more moderate compared to the planet's surface, which is hot enough to melt lead. The researchers estimated the concentration of phosphine to be around 20 parts per billion, a small but significant amount that sparked intense debate. The idea of life in Venus's atmosphere is not entirely new. Scientists have long speculated that the planet's clouds could harbor microbial life floating in droplets of sulfuric acid. These hypothetical organisms would need to be extremophiles, capable of surviving in highly acidic conditions and extreme temperatures. The detection of phosphine seemed to lend credibility to this theory, as no known non-biological process on Venus could easily explain its presence. However, the discovery was met with skepticism, with some researchers questioning the accuracy of the data or proposing alternative explanations, such as unknown chemical reactions or even volcanic activity. The debate over Venusian phosphine continues to this day. Follow-up observations have yielded conflicting results, with some studies confirming the presence of phosphine and others failing to detect it. The scientific community remains divided, with some researchers advocating for further investigation and others cautioning against jumping to conclusions. The mystery of Venus's Phosphine highlights the challenges of interpreting data from distant worlds and the need for more robust evidence before making definitive claims about extraterrestrial life. Future missions to Venus could help resolve this mystery. NASA Da Vinci and Veritas missions, as well as the European Space Agency's Envision mission, are set to explore Venus in the coming decades. These missions aim to study the planet's atmosphere, surface, and geological activity in unprecedented detail, potentially shedding light on the origin of Phosphine and whether it could indeed be linked to life. Until then, the Phosphine mystery remains one of the most intriguing and controversial questions in planetary science, reminding us that even our closest planetary neighbor holds secrets waiting to be uncovered. Now turning to the 28th of our 50 space mysteries, we venture closer to home, to the heart of our solar system, the Sun. One of the most baffling puzzles in solar physics is the solar corona heating problem. The Sun's corona, its outermost layer of atmosphere, is millions of degrees hotter than its surface, a fact that defies our basic understanding of heat and energy. While the Sun's surface, or photosphere, burns at around 5,500 degrees Celsius, the corona soars to temperatures exceeding 1 million degrees Celsius. This counterintuitive phenomenon has puzzled scientists for decades, as it seems to violate the laws of thermodynamics, which suggest that heat should decrease as you move away from a heat source. The leading theories to explain this mystery revolve around the Sun's magnetic fields and a phenomenon known as nanoflares. The Sun's magnetic field is incredibly dynamic, constantly twisting, breaking, and reconnecting due to the churning plasma beneath its surface. These magnetic interactions are thought to release vast amounts of energy in the form of tiny, frequent explosions called nanoflares. Each nanoflare is relatively small, but collectively, they could provide enough energy to heat the corona to its extreme temperatures. Think of it like a campfire. While a single spark might not produce much heat, countless sparks together could create a roaring blaze. Another theory involves magnetic waves, specifically Alfvén waves, which are ripples in the Sun's magnetic field. These waves are generated by the turbulent motion of plasma and can travel outward from the Sun's surface into the corona. As they propagate, they transfer energy, potentially heating the corona in the process. However, the exact mechanisms by which these waves deposit their energy remain unclear, leaving room for further investigation. Despite decades of research, the solar corona heating problem remains unsolved. Missions like NASA's Parker Solar Probe, which flies closer to the Sun than any spacecraft before it, are providing unprecedented data to help unravel this mystery. By studying the Sun's magnetic fields, plasma dynamics, and energy transfer processes, scientists hope to finally understand why the corona is so much hotter than the surface. This mystery not only challenges our understanding of the Sun, but also has broader implications for our knowledge of stars and plasma physics across the universe. As we continue to explore the Sun's secrets, the solar corona heating problem stands as a testament to the complexity and wonder of our nearest star. It reminds us that even the most familiar objects in the cosmos can hold profound mysteries, waiting for the right tools and minds to uncover them. Now turning to the 29th of our 50 space mysteries, we delve into another enigma of our Sun, the solar wind acceleration. The solar wind, a stream of charged particles constantly flowing from the Sun, races through space at speeds exceeding 1 million miles per hour. But how does this wind accelerate to such incredible velocities? This question has puzzled scientists for decades, as the mechanisms behind this phenomenon are not fully understood. At the heart of this mystery lies the Sun's magnetic field and the complex interactions between its plasma and magnetic forces. One key player in this process is magnetic reconnection, a phenomenon where magnetic field lines break and reconnect, releasing vast amounts of energy. This process can occur in the Sun's corona, where the magnetic field is highly dynamic and chaotic. When magnetic reconnection happens, it can propel charged particles outward, contributing to the acceleration of the solar wind. Think of it like a slingshot effect, where the sudden release of energy sends particles hurtling into space at tremendous speeds. Another factor in the solar wind's acceleration is the role of plasma waves, particularly Alfvén waves, which we touched on earlier. These waves, generated by the Sun's turbulent magnetic field, can carry energy from the Sun's surface into the corona and beyond. As these waves travel outward, they interact with the charged particles in the solar wind, transferring energy and helping to accelerate them. However, the exact details of how this energy transfer occurs remain a subject of ongoing research. Scientists are also exploring the role of the Sun's magnetic field in shaping the solar wind's structure and speed. The Sun's magnetic field is not uniform. It has regions of open and closed magnetic field lines. Open field lines extend far into space, allowing particles to escape more easily, while closed field lines trap particles closer to the Sun. The interplay between these regions influences the speed and density of the solar wind, adding another layer of complexity to this mystery. Missions like NASA's Parker Solar Probe are providing critical insights into the solar wind's acceleration. By flying closer to the Sun than any previous spacecraft, the probe is gathering data on the magnetic fields, plasma waves, and particle dynamics that drive the solar wind. These observations are helping scientists piece together the puzzle of how the solar wind accelerates to such high speeds, shedding light on one of the Sun's most enduring mysteries. The solar wind acceleration mystery is not just a scientific curiosity. It has real-world implications. The solar wind interacts with Earth's magnetic field, creating space weather that can affect satellites, communication systems, and even power grids. Understanding how the solar wind accelerates could improve our ability to predict and mitigate these effects, making it a crucial area of study. As we continue to explore the Sun's secrets, the solar wind acceleration mystery reminds us of the intricate and dynamic nature of our star. It's a testament to the fact that even the most familiar objects in the cosmos can hold profound mysteries, waiting for the right tools and minds to uncover them. Now turning to the 30th of our 50 space mysteries, we shift our focus to the Sun's magnetic field and its fascinating 11-year cycle. Every 11 years, the Sun undergoes a dramatic transformation, flipping its magnetic poles. North becomes south and south becomes north. This phenomenon, known as the solar magnetic cycle, is one of the most intriguing aspects of our star's behavior. Yet the exact mechanisms driving this flip remain a mystery. The Sun's magnetic field is generated by the motion of charged particles in its interior, a process called the solar dynamo. As these particles move and swirl, they create electric currents, which in turn generate magnetic fields. Over time, these fields become twisted and tangled, eventually leading to the magnetic pole reversal. But why does this happen every 11 years? Scientists believe it's tied to the Sun's internal dynamics, including the differential rotation of its layers. The equator rotates faster than the poles, and the complex interplay of plasma flows. However, the precise details of how these factors synchronize to produce the 11-year cycle are still not fully understood. The implications of the Sun's magnetic cycle extend far beyond the star itself. During the peak of the cycle, known as solar maximum, the Sun becomes more active, producing more sunspots, solar flares, and coronal mass ejections. These events can have significant effects on space weather, which in turn impacts Earth. For example, intense solar activity can disrupt satellite communications, interfere with GPS systems, and even pose risks to astronauts in space. On Earth, powerful solar storms can induce electric currents in power grids, potentially causing widespread blackouts. Understanding the Sun's magnetic cycle is therefore crucial for predicting and mitigating these effects. The Sun's magnetic field also plays a role in shaping Earth's climate. While the connection is complex and not yet fully understood, Some studies suggest that variations in solar activity over the 11-year cycle could influence atmospheric circulation patterns and even contribute to subtle changes in global temperatures. For instance, periods of low solar activity, such as the Maunder minimum in the 17th century, coincided with cooler global temperatures, while periods of high activity have been linked to warmer conditions. Unraveling this connection could provide valuable insights into both solar physics and climate science. Missions like NASA's Solar Dynamics Observatory and the upcoming European Space Agency's Solar Orbiter are providing unprecedented views of the Sun's magnetic field and its behavior. These observations are helping scientists piece together the puzzle of the 11-year cycle, shedding light on the processes that drive the Sun's magnetic reversals and their broader impact. The Sun's magnetic field is a reminder of the intricate and dynamic nature of our star. Its 11-year cycle not only shapes the Sun's activity, but also influences the space environment around Earth, affecting technology, climate, and even life itself. As we continue to study this cosmic phenomenon, we move closer to unlocking the secrets of the Sun and its profound connection to our planet. Now turning to the 31st of our 50 space mysteries, we delve into the enigmatic interiors of neutron stars. These incredibly dense remnants of supernova explosions pack the mass of a star into a sphere no larger than a city, creating conditions so extreme that they defy our understanding of matter itself. But what lies beneath the surface of these cosmic powerhouses? The answer remains one of the greatest unsolved puzzles in astrophysics. Neutron stars are so dense that a single teaspoon of their material would weigh billions of tons on Earth. This extreme density crushes atoms into a sea of neutrons, but what happens to matter under even greater pressure deep within the star? Scientists theorize that the core of a neutron star might contain exotic states of matter, such as quark-gluon plasma, a soup of fundamental particles that existed just moments after the Big Bang. In this state, protons and neutrons break down into their constituent quarks, creating a bizarre and unstable form of matter that we've only glimpsed in particle accelerators here on Earth. Another possibility is that the core might host hyperons particles made of quarks that are even stranger than the protons and neutrons we're familiar with. These hyperons could exist in a state of ultra-dense matter, governed by an equation of state that describes how matter behaves under such extreme conditions. However, the exact nature of this equation of state remains a mystery, as it depends on the fundamental properties of matter that we're still struggling to understand. The challenge of studying neutron star interiors lies in their inaccessibility. We can't send probes to these distant objects, so scientists rely on indirect methods, such as observing the gravitational waves emitted when neutron stars collide or measuring the precise timing of pulsar signals. These observations provide clues about the star's size, mass, and internal structure, but piecing together the full picture requires combining data from multiple sources and refining our theoretical models. Understanding the interiors of neutron stars isn't just an academic exercise. It has profound implications for our understanding of the universe. These stars are natural laboratories for testing the laws of physics under conditions that can't be replicated on Earth. By unraveling the mysteries of their cores, we could gain insights into the nature of matter, the behavior of quarks, and even the origins of the universe itself. As we continue to explore the depths of neutron stars, we're reminded of how much we still have to learn about the cosmos. These celestial objects, born from the ashes of dying stars, hold the keys to some of the most fundamental questions in science. And with each new discovery, we move closer to unlocking the secrets of the universe's most extreme environments. Now turning to the 32nd of our 50 space mysteries, we encounter the enigmatic and terrifying Magnetars. These neutron stars are not just incredibly dense, they also possess the most powerful magnetic fields in the known universe. Imagine a magnetic field so strong that it could strip the information off a credit card from halfway across the solar system. That's the kind of force we're talking about here. But what makes magnetars so magnetic, and why do they unleash such violent outbursts of energy? Magnetars are born from the same explosive supernova that create regular neutron stars, but something about their formation gives them these extraordinary magnetic fields. Scientists believe that during their birth, the chaotic collapse of the star's core twists and amplifies its magnetic field to unimaginable levels. The result is a magnetic field trillions of times stronger than Earth's, capable of distorting the very fabric of space-time around it. These extreme magnetic fields don't just sit quietly, they drive some of the most violent events in the universe. Magnetars are known for their sudden, intense bursts of energy called starquakes. These occur when the star's crust, under immense magnetic stress, cracks and releases a torrent of X-rays and gamma rays. In fact, some of the brightest gamma-ray bursts ever detected have been linked to magnetars. One such event, observed in 2004, released more energy in 1/10 of a second than our Sun emits in 100,000 years. Studying magnetars is no easy task. Their outbursts are unpredictable, and their extreme environments make them difficult to observe directly. Scientists rely on space-based telescopes to detect their high-energy emissions, but even then, the data is often fleeting and hard to interpret. Adding to the challenge is the fact that magnetars are relatively rare. Only about 30 have been identified so far in our galaxy. Despite these challenges, magnetars offer a unique window into the extremes of physics. Their magnetic fields push the limits of what we understand about electromagnetism and the behavior of matter under such conditions. By studying them, we can test theories about how magnetic fields are generated and how they interact with matter in ways that are impossible to replicate on Earth. The mystery of magnetars reminds us that the universe is full of phenomena that defy our expectations. These cosmic powerhouses, with their unimaginable magnetic fields and explosive outbursts, challenge our understanding of physics and inspire us to keep exploring the unknown. As we continue to study these enigmatic objects, we move closer to unraveling the secrets of the universe's most extreme environments. Now turning to the 33rd of our 50 space mysteries, we delve into the peculiar phenomenon of pulsar glitches. Pulsars, the rapidly spinning remnants of massive stars, are often referred to as cosmic lighthouses due to their incredibly precise and regular pulses of radiation. However, every now and then, these celestial timekeepers experience sudden, unexpected speed-ups in their rotation, known as glitches. These glitches, which can last from milliseconds to days, have puzzled scientists for decades as they defy the otherwise predictable behavior of these stellar objects. So, what causes these glitches? One leading theory involves the superfluid interior of pulsars. Deep within a pulsar, the core is thought to be composed of a superfluid, a state of matter that flows without friction. This superfluid is believed to be surrounded by a solid crust, and as the pulsar spins, the superfluid and crust rotate at slightly different rates. Over time, this mismatch can build up stress, causing the superfluid to transfer angular momentum to the crust in a sudden burst. This transfer results in the pulsar spinning faster, creating the glitch we observe. Another theory points to starquakes, similar to the violent crustal shifts seen in magnetars. Pulsars, with their incredibly dense and rigid crusts, can experience fractures due to the immense forces acting on them. When these fractures occur, the crust adjusts, causing a momentary change in the pulsar's rotation rate. These starquakes, while not as energetic as those in magnetars, could still explain some of the smaller glitches observed in pulsars. Studying pulsar glitches is no simple task. These events are unpredictable, and catching them in action requires constant monitoring of pulsars across the sky. When a glitch is detected, scientists analyze the changes in the pulsar's rotation and radiation to piece together what might have caused it. This data helps refine our understanding of the internal structure of pulsars and the exotic states of matter that exist within them. The mystery of pulsar glitches highlights the complexity of these stellar remnants and the extreme conditions they endure. By unraveling the secrets behind these sudden speed-ups, we gain deeper insights into the behavior of matter under conditions that are impossible to replicate on Earth. As we continue to study these cosmic anomalies, we move closer to understanding the intricate dance of forces that govern the universe's most enigmatic objects. Now turning to the 34th of our 50 space mysteries, we explore the incredible energy source behind quasars, some of the most luminous objects in the universe. Quasars, short for quasi-stellar radio sources, shine with a brilliance that can outshine entire galaxies, yet they are powered by regions no larger than our solar system. This immense energy output has baffled scientists for decades, raising the question, how can something so compact produce such staggering amounts of light and radiation? At the heart of every quasar lies a supermassive black hole, millions to billions of times more massive than our Sun. These cosmic giants are surrounded by swirling disks of gas and dust known as accretion disks. As material from the disk spirals inward toward the black hole, it heats up to extreme temperatures, emitting vast amounts of energy across the electromagnetic spectrum. This process converts gravitational energy into radiation, powering the quasar's incredible luminosity. But the mystery doesn't end there. While supermassive black holes and accretion disks explain much of a quasar's energy, the exact mechanisms behind their efficiency remain unclear. For instance, how do these black holes consume matter so rapidly, and what causes the jets of particles that shoot out from some quasars at nearly the speed of light? These jets, which can extend for thousands of light years, are thought to be powered by magnetic fields and the black hole's rotation, but the details are still a subject of intense research. Another puzzling aspect is the sheer scale of energy involved. Some quasars emit more energy in a single second than our Sun will produce in its entire lifetime. This raises questions about how such vast amounts of matter are funneled into the black hole and how the surrounding environment can sustain such extreme activity over billions of years. Studying quasars is like peering back in time, as their light often travels billions of years to reach us. By analyzing their spectra and behavior, scientists can learn not only about the quasars themselves, but also about the early universe and the formation of galaxies. Yet, despite decades of observation, the full picture of how quasars generate their immense energy remains incomplete. The mystery of quasar energy sources reminds us of the awe-inspiring power of supermassive black holes and the complex processes that govern the cosmos. As we continue to unravel the secrets of these luminous beacons, we gain a deeper understanding of the forces that shape the universe and the extreme conditions that exist at its most energetic frontiers. Now turning to the 35th of our 50 space mysteries, we delve into the enigmatic phenomenon of blazar jets. Blazars are a type of quasar, but with a unique twist. They shoot out highly energetic jets of particles directly toward Earth. These jets, traveling at nearly the speed of light, are among the most extreme and mysterious features in the universe. But how do they form, and what accelerates them to such incredible speeds? At the core of a blazar lies a supermassive black hole, much like those found in quasars. As matter spirals into the black hole, it forms an accretion disk, heating up and emitting vast amounts of energy. However, in blazars, some of this material doesn't fall into the black hole. Instead, it gets funneled into narrow, highly focused jets that blast outward from the poles of the black hole. These jets are so powerful that they can stretch across millions of light years, far beyond the boundaries of their host galaxies. The mystery lies in the mechanisms behind these jets. Scientists believe that magnetic fields play a crucial role in shaping and accelerating the particles. As the black hole spins, it twists the surrounding magnetic fields, creating a sort of cosmic slingshot that launches particles at relativistic speeds. But the exact process remains unclear. How do these magnetic fields become so strong, and what triggers the formation of the jets in the first place? Another puzzling aspect is the incredible energy these jets carry. Some blazar jets emit more energy than the entire galaxy that hosts them. This raises questions about how such vast amounts of energy are concentrated into such narrow streams. Additionally, the particles in these jets are accelerated to speeds so close to the speed of light that they defy our current understanding of physics. What forces are at work to push these particles to such extremes? Blazars also provide a unique window into the universe. Because their jets are pointed directly at us, we can observe them in incredible detail, making them invaluable for studying the physics of extreme environments. Yet, despite decades of research, the full story of blazar jets remains incomplete. They challenge our understanding of black holes, magnetic fields, and the behavior of matter under the most extreme conditions. The mystery of blazar jets reminds us of the universe's capacity for creating phenomena that push the boundaries of our knowledge. As we continue to study these cosmic powerhouses, we uncover not only the secrets of blazars but also the fundamental laws that govern the cosmos. Now turning to the 36th of our 50 space mysteries, we explore the awe-inspiring phenomenon of gamma-ray bursts. These are the most energetic explosions in the universe, releasing more energy in a few seconds than our sun will emit in its entire lifetime. But what causes these colossal bursts of radiation, and where do they come from? Gamma-ray bursts are thought to originate from two main sources: the mergers of neutron stars and the explosive deaths of massive stars known as hypernova. When two neutron stars spiral toward each other and collide, they create a cataclysmic event that sends out a short, intense burst of gamma rays. These mergers are also believed to produce gravitational waves, ripples in space-time that have been detected by observatories here on Earth. On the other hand, hypernova occur when a massive star, many times heavier than our Sun, exhausts its fuel and collapses under its own gravity. Instead of a typical supernova, the star undergoes a more violent explosion, launching jets of material at nearly the speed of light. These jets, if pointed toward Earth, produce the long gamma-ray bursts we observe. The sheer power of these events is staggering, often outshining entire galaxies for a brief moment. Yet, despite their incredible energy, gamma-ray bursts remain shrouded in mystery. Why do some massive stars produce hypernova while others do not? What exactly happens during the milliseconds of a neutron-star merger that triggers such a powerful burst? And how do these events manage to focus their energy into such narrow, intense beams? Scientists are also intrigued by the afterglows of gamma-ray bursts, which can be observed in X-rays, visible light, and radio waves. These afterglows provide clues about the environments where the bursts occur and the nature of the explosions themselves. However, the fleeting nature of gamma-ray bursts makes them difficult to study. By the time telescopes detect them, the bursts are often already fading. Gamma-ray bursts are not just cosmic curiosities, they also serve as probes of the distant universe. Because they are so bright, they can be seen from billions of light-years away, offering a glimpse into the early universe and the conditions that existed shortly after the Big Bang. Yet, their origins and mechanisms continue to challenge our understanding of physics and the cosmos. As we unravel the mysteries of gamma-ray bursts, we gain deeper insights into the most extreme events in the universe. These cosmic explosions remind us of the universe's capacity for both creation and destruction, pushing the boundaries of what we thought was possible. Now turning to the 37th of our 50 space mysteries, we delve into the enigmatic world of cosmic rays. These are not your ordinary rays of light or radiation. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. Some of these particles carry energies millions of times greater than anything we can produce in our most powerful particle accelerators on Earth. But where do these ultra-high-energy cosmic rays come from, and how do they reach such incredible speeds? The origins of cosmic rays have puzzled scientists for over a century. While lower-energy cosmic rays are thought to come from sources like the Sun or supernova remnants, the ultra-high-energy ones are a different story. These particles are so energetic that their sources must be incredibly powerful, yet pinpointing exactly where they originate has proven to be a monumental challenge. One leading theory suggests that supermassive black holes lurking at the centers of galaxies could be the culprits. As these black holes devour matter, they create jets of particles that are accelerated to extreme speeds, potentially producing the cosmic rays we detect. Another possibility involves active galactic nuclei, where the intense gravitational and magnetic fields around supermassive black holes could act as natural particle accelerators. These environments are so extreme that they can hurl particles across the universe with unimaginable energy. However, tracing these cosmic rays back to their sources is no easy task. Unlike light, which travels in straight lines, cosmic rays are charged particles, meaning they are deflected by magnetic fields as they journey through space. This makes their paths unpredictable and their origins difficult to pinpoint. Adding to the mystery is the fact that ultra-high-energy cosmic rays are incredibly rare. Detecting them requires massive observatories like the Pierre Auger Observatory in Argentina, which uses an array of detectors spread over thousands of square kilometers to catch these elusive particles. Even then, scientists can only observe the secondary particles created when cosmic rays collide with Earth's atmosphere, making it even harder to trace their origins. Despite these challenges, studying cosmic rays offers a unique window into the most violent and energetic processes in the universe. They provide clues about the nature of supermassive black holes, the structure of magnetic fields in space, and even the composition of matter itself. As we continue to unravel the mystery of cosmic rays, we edge closer to understanding the forces that shape our universe and the incredible phenomena that occur within it. Now turning to the 38th of our 50 space mysteries, we explore one of the most profound questions in modern physics. Why does our universe consist almost entirely of matter with almost no antimatter? According to our current understanding of particle physics, matter and antimatter should have been created in equal amounts during the Big Bang. Yet, when matter and antimatter meet, they annihilate each other, leaving behind only energy. So, if equal amounts were produced, why didn't the universe annihilate itself entirely? This puzzling imbalance is one of the greatest unsolved mysteries in science. The key to this mystery may lie in a phenomenon known as CP violation. CP stands for charge parity, a symmetry that, if perfectly preserved, would mean that the laws of physics should treat matter and antimatter identically. However, experiments have shown that this symmetry is not perfect. Tiny differences in how matter and antimatter behave could explain why matter survived in greater quantities after the Big Bang. One of the most famous examples of CP violation was observed in the behavior of particles called kaons and B mesons, which decay slightly differently depending on whether they are matter or antimatter. These subtle differences, though small, could have tipped the scales in favor of matter during the universe's earliest moments. Another theory suggests that the imbalance might be linked to the extreme conditions of the early universe. In the first fractions of a second after the Big Bang, the universe was a seething cauldron of energy and particles. During this time, processes like baryogenesis, the creation of more baryons or matter particles than antibaryons, could have occurred. Some models propose that exotic particles or forces not yet discovered played a role in this process. For instance, the hypothetical neutrino, known as a sterile neutrino, could have interacted in ways that favored the production of matter over antimatter. Despite decades of research, the antimatter imbalance remains unresolved. Experiments like those conducted at CERN Large Hadron Collider are searching for clues by recreating the conditions of the early universe and studying the behavior of particles and antiparticles with incredible precision. Meanwhile, observations of cosmic rays and gamma rays are helping scientists look for signs of antimatter in distant regions of the universe where it might still exist in small quantities. Understanding why matter dominates over antimatter is not just a question of curiosity, it's fundamental to our understanding of the universe itself. If the balance had been even slightly different, the cosmos as we know it might not exist at all. As we continue to probe this mystery, we inch closer to uncovering the secrets of the universe's origins and the forces that shaped its evolution. Now turning to the 39th of our 50 space mysteries, we delve into the mind-bending concept of quantum foam. Imagine the fabric of space-time not as a smooth, continuous surface, but as a frothy, turbulent sea at the tiniest scales imaginable. This is the essence of quantum foam, a theoretical idea that suggests space-time itself is not perfectly smooth, but instead fluctuates wildly at scales so small they are almost impossible to measure. These fluctuations are thought to occur at the Planck scale, which is about 1/trillionth of a trillionth of the size of an atom. At this level, the very structure of space-time becomes chaotic, with tiny bubbles of energy popping in and out of existence. Quantum foam is a key concept in the quest to unify quantum mechanics and general relativity, two of the most successful but seemingly incompatible theories in physics. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity describes the force of gravity and the large-scale structure of the universe. Quantum foam arises from the idea that, at these minuscule scales, the smooth spacetime described by Einstein's theory breaks down, giving way to a turbulent, ever-changing landscape. This chaotic behavior could hold the key to understanding quantum gravity, a theory that would explain how gravity works at the quantum level. One of the most intriguing implications of quantum foam is its potential impact on our understanding of reality itself. If spacetime is not smooth but instead a seething, frothy sea, it challenges our classical notions of space and time as fixed and absolute. Instead, spacetime could be dynamic and fluctuating, with particles and energy appearing and disappearing in a constant dance. This idea also raises questions about the nature of black holes and the singularity at their centers, where the laws of physics as we know them break down. Could quantum foam provide a way to resolve the paradoxes that arise in these extreme environments? Despite its theoretical appeal, quantum foam remains one of the most elusive concepts in physics. Directly observing these fluctuations is currently beyond our technological capabilities, as they occur at scales far smaller than anything we can measure. However, scientists are exploring indirect ways to detect the effects of quantum foam, such as by studying the behavior of particles or looking for tiny distortions in the light from distant stars. These efforts could one day provide evidence for this strange and fascinating idea, shedding light on the true nature of space-time and the universe itself. As we continue to explore the mysteries of quantum foam, we are reminded of how much we still have to learn about the fundamental nature of reality. This concept not only challenges our understanding of space and time, but also opens up new possibilities for uncovering the secrets of the cosmos. With each step forward, we come closer to unraveling the profound mysteries that lie at the heart of existence. Now turning to the 40th of our 50 space mysteries, we explore the mind-bending idea of the holographic principle. This concept suggests that the universe as we perceive it might actually be a hologram, a two-dimensional projection of information encoded on a distant boundary. At first glance, this idea seems straight out of science fiction, but it emerges from serious scientific inquiry into the nature of black holes and the fundamental laws of physics. The holographic principle has its roots in black hole physics, particularly in the work of physicist Stephen Hawking. Hawking discovered that black holes emit radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. This raised a puzzling question. What happens to the information about the matter that falls into a black hole? According to quantum mechanics, information cannot be destroyed, but black holes seem to defy this rule. The holographic principle offers a potential solution. It proposes that all the information about the matter swallowed by a black hole is not lost but instead encoded on its event horizon, the boundary beyond which nothing can escape. In this view, the event horizon acts like a cosmic hard drive, storing the information in a two-dimensional form. This idea extends beyond black holes to the universe as a whole. The holographic principle suggests that the entire cosmos could be a projection of information stored on a two-dimensional surface at its boundary. In other words, the three-dimensional reality we experience might be a kind of illusion, like a hologram emerging from a flat surface. This concept challenges our everyday understanding of space and dimensions, suggesting that the universe operates more like a computer simulation than a physical, tangible entity. One of the most fascinating implications of the holographic principle is its connection to the nature of information. If the universe is fundamentally a hologram, then information becomes the most basic building block of reality. This idea aligns with emerging theories in quantum gravity, which seek to unify quantum mechanics and general relativity. The holographic principle provides a framework for understanding how information is preserved and processed in the universe, offering new insights into the nature of spacetime itself. Despite its profound implications, the holographic principle remains a theoretical concept. Testing it experimentally is incredibly challenging, as it requires observing phenomena at scales far beyond our current technological capabilities. However, scientists are exploring ways to test the principle indirectly, such as by studying the cosmic microwave background radiation or analyzing the behavior of particles in high-energy experiments. These efforts could one day provide evidence for this radical idea, reshaping our understanding of reality. As we ponder the holographic principle, we are reminded of how much the universe still has to teach us. This concept not only challenges our perception of space and dimensions, but also invites us to rethink the very nature of existence. With each step forward, we come closer to uncovering the profound mysteries that lie at the heart of the cosmos. Now turning to the 41st of our 50 space mysteries, we delve into the mind-expanding concept of the multiverse hypothesis. This idea suggests that our universe might not be the only one in existence. Instead, it could be just one of countless universes, each with its own unique set of physical laws and properties. The multiverse hypothesis challenges our understanding of reality, proposing that what we perceive as the entire cosmos might be just a tiny fraction of a much larger, more complex structure. The multiverse hypothesis arises from several areas of theoretical physics, including quantum mechanics, string theory, and cosmology. One of the most well-known versions of this idea comes from the theory of cosmic inflation, which describes the rapid expansion of the universe just after the Big Bang. According to this theory, different regions of space could have expanded at different rates, creating bubbles of space-time that developed into separate universes. Each of these universes could have its own distinct physical constants, particles, and even dimensions, making them vastly different from our own. Another version of the multiverse idea comes from quantum mechanics, specifically the many worlds interpretation. This interpretation suggests that every time a quantum event occurs, such as the decay of a radioactive atom, the universe splits into multiple branches, each representing a different outcome. In this view, every possible outcome of every quantum event exists in its own separate universe, leading to an infinite number of parallel realities. While this idea is fascinating, it remains purely theoretical, as there is currently no way to observe or interact with these other universes. the multiverse hypothesis also raises profound philosophical questions. If there are infinite universes, does that mean every possible version of reality exists somewhere? Could there be universes where history unfolded differently, or where the laws of physics allow for phenomena we can't even imagine? These questions challenge our notions of uniqueness and purpose, suggesting that our universe might be just one of many possible outcomes in a vast cosmic landscape. Despite its intriguing possibilities, the multiverse hypothesis remains controversial. Critics argue that it is untestable and therefore falls outside the realm of science. After all, if we can't observe or interact with other universes, how can we ever prove they exist? Supporters, however, point to indirect evidence, such as anomalies in the cosmic microwave background radiation or the fine-tuning of physical constants, as potential hints of a multiverse. While these clues are far from conclusive, they keep the idea alive as a subject of ongoing research and debate. As we explore the multiverse hypothesis, we are reminded of the boundless possibilities that lie beyond our current understanding. This concept not only challenges our perception of reality, but also invites us to imagine a cosmos far more vast and diverse than we ever thought possible. With each new discovery, we inch closer to unraveling the mysteries of existence, whether they lie within our universe or beyond it. Now turning to the 42nd of our 50 space mysteries, we confront one of the most profound questions in cosmology: what caused the Big Bang, and what, if anything, existed before it? The Big Bang singularity represents the moment when our universe began, a point of infinite density and temperature where the laws of physics as we know them break down. But what triggered this explosive beginning, and what lies beyond the veil of that singular moment? One of the leading theories attempting to explain the Big Bang singularity involves quantum fluctuations. In the realm of quantum mechanics, particles can spontaneously appear and disappear in a vacuum, a phenomenon known as quantum foam. Some scientists propose that a quantum fluctuation in a pre-existing state of nothingness could have sparked the Big Bang, creating the universe from a tiny, unstable bubble of energy. This idea suggests that our universe might have emerged from a random, yet inevitable quantum event, challenging our understanding of cause and effect. Another intriguing theory is the concept of cyclic universes, which proposes that the Big Bang was not a one-time event but part of an endless cycle of cosmic birth, death, and rebirth. According to this model, our universe expands, contracts, and then explodes again in a new Big Bang, repeating the process indefinitely. This idea draws from the observation that the universe's expansion is accelerating, raising the possibility that it could eventually collapse back on itself, leading to a new cycle. While this theory offers a way to avoid the singularity problem, it remains speculative as we have no direct evidence of previous cycles. The Big Bang singularity also raises the question of what, if anything, existed before it. Some theories suggest that time itself began with the Big Bang, meaning there was no before in the conventional sense. Others propose the existence of a multiverse, where our universe is just one of many, each with its own Big Bang. In this view, the singularity might mark the boundary between our universe and a larger, more complex reality. Despite decades of research, the mystery of the Big Bang singularity remains unsolved. The extreme conditions of the early universe make it difficult to study directly, and our current understanding of physics is insufficient to describe what happened at that moment. However, advancements in quantum gravity and cosmology continue to push the boundaries of our knowledge, offering new insights into the origins of our universe. As we ponder the Big Bang singularity, we are reminded of the limits of human understanding and the vastness of the unknown. This mystery not only challenges our scientific theories but also invites us to imagine the unimaginable, exploring the very edges of existence itself. With each new discovery, we come closer to unraveling the secrets of the cosmos, one singularity at a time. Now turning to the 43rd of our 50 space mysteries, we delve into the ultimate fate of the universe itself. What lies at the end of time? Will the cosmos continue to expand forever, or will it collapse back in on itself? These questions lead us to two of the most widely discussed scenarios, the Big Freeze and the Big Crunch, both of which hinge on the enigmatic force known as dark energy. The Big Freeze, also called the heat death of the universe, paints a picture of a cold, dark, and lonely end. In this scenario, the universe continues to expand at an accelerating rate driven by dark energy. Over trillions of years, galaxies will drift farther apart, stars will burn out, and black holes will evaporate. Eventually, the universe will reach a state of maximum entropy, where no usable energy remains and all activity ceases. It's a chilling vision of a universe that simply fades into silence. On the other hand, the Big Crunch offers a dramatically different outcome. If dark energy weakens over time, or if the universe's expansion slows down, gravity could eventually take over, pulling everything back together. Galaxies, stars, and even atoms would collapse into a single point of infinite density, mirroring the Big Bang in reverse. This cyclical model suggests that the universe might not have a true end, but instead undergoes endless cycles of expansion and contraction, a cosmic dance of creation and destruction. The role of dark energy is central to determining which of these fates awaits our universe. Discovered in the late 1990s, dark energy is the mysterious force driving the accelerated expansion of the cosmos. If it remains constant or grows stronger, the Big Freeze becomes the likely outcome. However, if dark energy diminishes or changes in some unexpected way, the Big Crunch could come into play. Scientists are still working to understand the true nature of dark energy, making it one of the most critical puzzles in modern cosmology. Beyond these two scenarios, other theories propose even more exotic possibilities, such as the Big Rip, where dark energy becomes so dominant that it tears apart galaxies, stars, and even atoms. Or the idea of a multiverse, where our universe is just one of many, each with its own unique fate. While these ideas remain speculative, they highlight the profound uncertainty surrounding the ultimate destiny of the cosmos. As we contemplate the end of the universe, we are reminded of the fleeting nature of existence and the vast scales of time and space. Whether the universe ends in a freeze, a crunch, or something entirely unexpected, these mysteries challenge us to think beyond our lifetimes and even beyond the lifespan of stars and galaxies. They invite us to explore the deepest questions about the nature of reality and our place within it. And as we continue to probe the cosmos, each discovery brings us closer to understanding not just how the universe began, but how it might one day end. Now turning to the 44th of our 50 space mysteries, we explore the intriguing concept of white holes, the theoretical opposites of black holes. While black holes are known for their immense gravitational pull, from which nothing, not even light, can escape, white holes are imagined as cosmic objects that expel matter and energy instead of consuming them. Think of them as the universe's way of giving back, a kind of cosmic fountain that spews out everything it contains. The idea of white holes arises from the equations of general relativity, the same framework that predicts black holes. In theory, if a black hole is a one-way street into oblivion, a white hole would be a one-way street out of it. Some scientists speculate that white holes could be the other end of a black hole, connected by a theoretical tunnel through space-time known as a wormhole. This would mean that anything swallowed by a black hole might eventually be ejected by a white hole somewhere else in the universe, or even in another universe entirely. However, white holes remain purely hypothetical. Unlike black holes, which have been observed indirectly through their effects on surrounding matter and light, white holes have never been detected. One reason for this is that white holes, if they exist, would likely be extremely unstable. The laws of physics suggest that they would collapse almost instantly, making them nearly impossible to observe. But if they do exist, how might we detect them? Scientists propose that white holes could emit bursts of energy or particles, creating unique signatures that telescopes and detectors could potentially pick up. These signals would be unlike anything else in the cosmos, offering a tantalizing clue to their existence. The study of white holes also ties into broader questions about the nature of space-time and the universe. If white holes are real, they could provide insights into the behavior of singularities, the mysterious points of infinite density at the centers of black holes. They might also help us understand the origins of the universe itself, with some theories suggesting that the Big Bang could have been a kind of white hole event, spewing out the matter and energy that formed our cosmos. While the white hole hypothesis remains speculative, it challenges our understanding of the universe and pushes the boundaries of theoretical physics. Whether or not white holes exist, the concept invites us to imagine new possibilities and explore the strange, counterintuitive nature of the cosmos. As we continue to probe the mysteries of black holes, wormholes, and spacetime itself, the search for white holes reminds us that the universe is full of surprises waiting to be discovered. Now turning to the 45th of our 50 space mysteries, we delve into the fascinating concept of wormholes, hypothetical tunnels through spacetime that could serve as shortcuts across vast cosmic distances. Imagine being able to travel from one end of the galaxy to another in an instant, bypassing the limitations of light speed. This is the tantalizing promise of wormholes, a concept rooted in the equations of general relativity. Wormholes, also known as Einstein-Rosen bridges, are theorized to connect two distant points in spacetime, creating a bridge that could drastically reduce travel time. While black holes pull everything in and white holes expel matter, wormholes offer a two-way passage, potentially linking different regions of the universe, or even different universes altogether. The idea is both thrilling and mind-bending, suggesting that the fabric of spacetime might be far more intricate than we currently understand. However, the existence of wormholes comes with significant challenges. For one, they are predicted to be incredibly unstable. Without some form of exotic matter or negative energy to hold them open, wormholes would collapse almost instantly, making them useless for travel. Exotic matter, which defies the normal rules of physics by having negative mass or energy, is purely theoretical and has never been observed. Even if we could find or create such matter, stabilizing a wormhole would require an unimaginable amount of energy, far beyond our current technological capabilities. Another major hurdle is the potential for time travel. If wormholes connect not just space but also time, they could theoretically allow for journeys into the past or future. This raises a host of paradoxes, such as the famous grandfather paradox, where a time traveler could potentially alter events in a way that prevents their own existence. These paradoxes challenge our understanding of causality and the fundamental laws of physics, making the idea of wormhole-based time travel both exciting and deeply problematic. Despite these challenges, the study of wormholes continues to captivate scientists and science fiction enthusiasts alike. They represent a frontier of theoretical physics, pushing us to rethink the nature of spacetime and the limits of human exploration. While we have yet to find any evidence of wormholes, their theoretical existence inspires us to dream of a future where the cosmos is more interconnected than we ever imagined. As we ponder the mysteries of wormholes, we are reminded that the universe is full of possibilities that defy our current understanding. Whether or not wormholes exist, the pursuit of such ideas drives us to explore, question, and imagine the extraordinary. And with that, we move forward to the next mystery, where even more cosmic wonders await. Now turning to the 46th of our 50 space mysteries, we explore the fascinating discovery of time crystals, a groundbreaking new phase of matter that challenges our understanding of physics. Unlike ordinary crystals, which have repeating patterns in space, time crystals exhibit repeating patterns in time, creating a structure that oscillates without any external energy input. This bizarre behavior defies the traditional laws of thermodynamics, making time crystals one of the most intriguing discoveries in modern science. Time crystals were first theorized in 2012 by Nobel laureate Frank Wilczek, who proposed the idea of a system that could break time symmetry, much like how ordinary crystals break spatial symmetry. In 2016, researchers successfully created time crystals in the lab using chains of ions or defects in diamond lattices. These experiments confirmed that time crystals could indeed exist, marking a major milestone in the study of quantum systems. What makes time crystals so unique is their ability to maintain periodic motion in their ground state, the lowest energy state possible. This means they can oscillate indefinitely without losing energy, a property that seems to defy the second law of thermodynamics. While this doesn't violate the laws of physics, since no energy is being created or destroyed, it does open up new possibilities for understanding the fundamental nature of matter and energy. One of the most exciting potential applications of time crystals lies in the field of quantum computing. Their stable, periodic behavior could be harnessed to create more robust quantum systems, reducing errors and improving the efficiency of quantum calculations. This could revolutionize fields like cryptography, materials science, and artificial intelligence, paving the way for technologies that were once thought to be the stuff of science fiction. However, the study of time crystals is still in its early stages, and many questions remain unanswered. How can we scale up their production? What other properties might they exhibit? And could they help us uncover deeper truths about the nature of time itself? As researchers continue to explore these questions, time crystals remind us that the universe is full of surprises waiting to be discovered. With this glimpse into the strange world of time crystals, we move forward to the next mystery where even more cosmic wonders await. Now turning to the 47th of our 50 space mysteries, we delve into the mind-bending phenomenon of quantum entanglement, a cornerstone of quantum mechanics that continues to baffle scientists and challenge our understanding of reality. Quantum entanglement occurs when two or more particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This connection seems to defy the speed of light, raising profound questions about the nature of space, time, and communication. The concept of quantum entanglement was first proposed in the early 20th century as part of the development of quantum theory. Albert Einstein famously referred to it as spooky action at a distance, expressing his discomfort with the idea that particles could influence each other instantaneously across vast distances. Despite his skepticism, experiments over the decades have repeatedly confirmed that entanglement is real. In fact, it has become a key tool in cutting-edge technologies like quantum computing and quantum cryptography. One of the most puzzling aspects of quantum entanglement is its apparent violation of the principle that nothing can travel faster than the speed of light. When two entangled particles are measured, the results are correlated in a way that suggests information is being shared instantaneously. However, this doesn't mean we can use entanglement to send messages faster than light. The correlations between entangled particles are random, and no useful information can be transmitted without additional communication through conventional means. This limitation has led to intense debates about whether entanglement truly allows for faster-than-light communication, or if it simply reveals a deeper, hidden layer of reality. The implications of quantum entanglement extend far beyond theoretical physics. If we could harness its full potential, it could revolutionize fields like secure communication, where entangled particles could be used to create unbreakable encryption. It could also lead to breakthroughs in quantum computing, where entangled qubits could perform calculations at speeds unimaginable with classical computers. Yet, despite its promise, entanglement remains one of the most enigmatic phenomena in science, with many questions still unanswered. How does entanglement work on a fundamental level? What does it tell us about the nature of reality? And could it ever be used to achieve faster than light communication? As we continue to explore these questions, quantum entanglement reminds us that the universe is far stranger and more interconnected than we ever imagined. With this mystery still unfolding, we move forward to the next cosmic enigma, where even more astonishing discoveries await. Now turning to the 48th of our 50 space mysteries, we explore the intriguing and controversial simulation hypothesis. This idea suggests that our entire universe, including everything we see, feel, and experience, might be an incredibly advanced computer simulation created by a higher intelligence. While it may sound like science fiction, this hypothesis has gained serious attention from scientists, philosophers, and even tech entrepreneurs, sparking debates about the nature of reality itself. The simulation hypothesis draws on the rapid advancements in computing power and virtual reality. If future civilizations could create simulations indistinguishable from reality, it's possible that we are living in one of those simulations right now. Philosopher Nick Bostrom formalized this idea in 2003, proposing that at least one of three possibilities must be true. Either advanced civilizations never reach the stage where they can create such simulations, they choose not to create them, or we are almost certainly living in one. This trilemma has become a cornerstone of the debate, with many arguing that the third option is the most plausible. But what evidence, if any, supports this idea? Some scientists point to the strange behavior of particles at the quantum level, where reality seems to operate more like a computer program than a physical system. For example, the way particles only decide their properties when observed could be interpreted as a way for the simulation to save processing power. Others suggest that the mathematical nature of the universe, with its precise laws and constants, hints at a designed system rather than a random occurrence. However, these arguments remain speculative, and there is no definitive proof to confirm or refute the simulation hypothesis. The philosophical implications of this idea are profound. If our reality is a simulation, it raises questions about free will, the nature of consciousness, and the purpose of existence. Are we merely characters in a cosmic game, or do we have genuine autonomy? Could the creators of the simulation intervene in our lives, or are they indifferent observers? These questions challenge our understanding of what it means to be real and force us to reconsider our place in the universe. Despite its speculative nature, the simulation hypothesis continues to captivate our imagination and push the boundaries of science and philosophy. Whether or not we are living in a simulation, the idea invites us to think deeply about the nature of reality and the limits of human knowledge. As we ponder this cosmic mystery, we move forward to the next enigma, where even more astonishing possibilities await. Now turning to the 49th of our 50 space mysteries, we delve into the fascinating Drake equation, a formula designed to estimate the number of intelligent civilizations that might exist in our galaxy. Proposed by astronomer Frank Drake in 1961, this equation has become a cornerstone in the search for extraterrestrial life, sparking both scientific inquiry and philosophical debate. The Drake equation multiplies several factors to arrive at an estimate of how many advanced civilizations could be out there. These factors include the rate of star formation, the fraction of stars with planetary systems, the number of planets that could support life, the likelihood of life developing on those planets, the probability of that life evolving intelligence, the ability of intelligent civilizations to communicate across space, and the lifespan of such civilizations. While the equation itself is straightforward, each factor is filled with uncertainty, making the final estimate highly speculative. For example, we now know that many stars host planets, thanks to discoveries by missions like the Kepler Space Telescope. But how many of these planets are truly habitable, And even if life emerges, what are the odds it evolves into intelligent beings capable of communication? These questions remain unanswered, leaving the Drake equation more of a thought experiment than a precise calculation. Estimates range from just a handful of civilizations to millions scattered across the Milky Way. The search for extraterrestrial intelligence, or SETI, has been heavily influenced by the Drake equation. Projects like the Allen Telescope Array and Breakthrough Listen aim to detect signals from advanced civilizations, but so far the universe has remained silent. This silence has led to new questions, such as whether intelligent life is rare, short-lived, or simply too far away to detect with our current technology. Despite its uncertainties, the Drake equation continues to inspire scientists and dreamers alike. It reminds us of the vastness of the cosmos and the possibility that we are not alone. As we ponder the mysteries of intelligent life beyond Earth, we move forward to the final enigma in our list, where even more profound questions await. Now turning to the 50th and final mystery on our list, we explore the intriguing zoo hypothesis. This idea suggests that advanced extraterrestrial civilizations might be deliberately avoiding contact with us, much like how humans observe animals in a zoo without interfering. The hypothesis offers a potential explanation for the Fermi Paradox, which questions why, given the vastness of the universe, we have yet to encounter any signs of intelligent alien life. The zoo hypothesis proposes that these advanced civilizations might be intentionally hiding their presence, either to allow humanity to develop naturally or to avoid causing disruption to our society. It's a thought-provoking concept that shifts the focus from the absence of evidence to the possibility of deliberate concealment. Could it be that we are being observed from afar, with extraterrestrial beings choosing to remain silent for reasons beyond our understanding? This idea has significant implications for the search for extraterrestrial intelligence, or SETI. If advanced civilizations are intentionally avoiding contact, our efforts to detect them through radio signals or other means might be futile. It raises questions about the nature of intelligence and the ethical considerations that might guide an advanced species' interactions with less developed ones. Are we being watched, studied, or simply left alone to evolve on our own timeline? The zoo hypothesis also ties back to the Fermi Paradox, offering a potential resolution to the puzzling silence of the cosmos. Instead of assuming that intelligent life is rare or short-lived, this theory suggests that the universe might be teeming with civilizations that have chosen to remain hidden. It challenges us to rethink our assumptions about contact and consider the possibility that we are part of a much larger, yet unseen, cosmic community. As we conclude our journey through these 50 space mysteries, the zoo hypothesis leaves us with a profound sense of wonder and curiosity. It reminds us that the universe is full of possibilities, many of which remain beyond our current understanding. Whether or not advanced civilizations are out there, watching us from the shadows, the search for answers continues to inspire and challenge us. Thank you for joining us on this exploration of the cosmos, and don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of the universe. Until next time, keep looking up. Now turning to the conclusion of our cosmic journey, we reflect on the 50 space mysteries that have captivated our imaginations and challenged our understanding of the universe. From the Fermi Paradox to the zoo hypothesis, each mystery has revealed the vastness of the unknown and the limits of our current knowledge. These enigmas remind us that the cosmos is far more complex and mysterious than we can comprehend, filled with phenomena that defy explanation and invite endless curiosity. Throughout this exploration, we've encountered questions that push the boundaries of science and philosophy. Why does dark matter remain invisible? What powers the enigmatic quasars? Are we alone in the universe, or are advanced civilizations watching us from the shadows? These mysteries not only highlight the gaps in our understanding, but also inspire us to keep searching, questioning, and exploring. They remind us that the universe is a place of infinite wonder, where every discovery leads to new questions and deeper mysteries. As we wrap up this journey, we encourage you to stay curious and keep looking up. The universe is vast and its secrets are waiting to be uncovered. Share your thoughts on these mysteries in the comments below. What fascinates you the most? Which theories do you find most compelling? And don't forget to like, subscribe, and hit the notification bell so you never miss an exploration into the wonders of the cosmos. Thank you for joining us on this adventure through the stars. Until next time, keep wondering, keep exploring, and keep reaching for the unknown. The universe is waiting.